So today I would like to present the computational techniques that we have been developing over the past few years to bridge the quantum mechanical length scale with the continuum length scale and make possible electronic structure calculations at macroscopic scales. So this is work with my students, Mrinal Iyer, Balachandran Radhakrishnan, and Fani Mottamari. So the main motivation for this work comes from understanding defects in materials. And defects, as we all know, play a very important role in influencing a wide range of material properties, be it mechanical, be it electronic, optical, or chemical. So for instance, like dislocations, which are line defects in crystalline materials, they result in significant drop of the strength of the materials to about 1,000 of what is theoretically possible. And point defects like vacancies and self-interstitials, these are responsible for influencing a wide range of mechanical properties like creep, spalling, aging, and radiation hardening. And then you could have like interfaces which would affect like chemical reactivity, ferroelectric domain walls, which result in the hysteresis in ferroelectric switching, and the list goes on. So when we want to understand like the defects in materials and their behavior is governed by the energetics of defects. And very loosely speaking, we can think about the energetics having like two contributions. One is what happens at the core, in which in continuum mechanics, we just call it the core energy. And the other is basically the elastic interactions which the defects produce, which contributes to the elastic energy of the defect. So if we actually look very closely, there are a vast span of interacting length scales which become important. So at the core, where you're talking about length scales of the order of angstroms, the electronic structure of the core is very important. And then there is the complex rearrangement of atoms that happen, which comes from the electronic structure of the core itself. And then further, these rearrangements of atoms result in a long-range elastic field, which can go up to like micron length scales. So we're talking about a vast span of length scales over here. And the more complex part of this is that when we're looking at defects, these length scales are actually interacting length scales. And I'll present like some examples which demonstrate this aspect. And the other challenging part about defects is that the realistic defect concentration in materials is about few parts per million. So we have about a few defects in a million atoms. And yet these things significantly result in macroscopic properties. So if we have to understand from a predictive viewpoint the energetics of defects, we should be able to like conduct these electronic structure calculations at macroscopic scales, because the fundamental theory in all these length scales is actually the quantum mechanical interactions. So the way we achieve this is by systematic coarse graining using adaptive numerical methods. So hopefully I've given you a motivation for the talk that I'm going to present. I'll now provide a very brief introduction to electronic structure calculations just to set the tone of the presentation. And then I'll discuss what is called as orbital free density functional theory, which is an approximation to the more widely accepted Kohn-Sham density functional theory, which is applicable to material systems which are close to a free electron gas. So it's applicable to material systems like aluminum, magnesium, and so forth. Then I will present this coarse graining scheme, which we call as the quasi-continuum orbital free density functional theory, which is a seamless way to get to much larger systems, and we can look at defects in materials. And then I will demonstrate illustrative examples which show the convergence properties of this method, as well as the effectiveness of this method by looking at the energetics of vacancies, and as well as I'll present like our recent results on dislocation core studies. And then if time permits, I will also like talk about extensions to Kohn-Sham DFT that we are pursuing in the past few years. So the starting point of all electronic structure calculations is the Schrodinger equation. And the Schrodinger equation is nothing but the solution of an eigenvalue problem, h psi is equal to E psi, where h is the Hamiltonian, psi is the wave function of the eigenvector, E is the energy of the system or the eigenvalue, and this Hamiltonian h has various components. The first term over here is the kinetic energy of electrons. And if we have n electrons in the system, we have n Laplace operators. The second term over here is the kinetic energy of the nuclei, where Ma is the mass of an eighth nucleus. And this term over here is the electrostatic interaction between the electrons and the nuclei. This is the electrostatic interaction between the electrons, and this is the electrostatic interaction between the nuclei. And if we look at the wave function is dependent on the position as well as the spin of the n electrons, as well as the positions of the m nuclei, which are, so the positions of the electrons are denoted by little r's, and the positions of the nuclei are denoted by capital R's. And what is conventional in quantum mechanics is to do what is called as the Born-Oppenheimer Approximation. And what this approximation says is that the nuclei are much more massive than electrons, like almost 1,000 times more massive. So the kinetic energy of this nuclei can be ignored in comparison to the kinetic energy of the electrons. And then you can treat this wave function to be quasi-statically dependent on the positions of the m nuclei. So the wave function then becomes a function only of the positions of the n electrons and a parametric dependence on the position of the m nuclei. But if you look at the complexity of this calculation, well, I should be careful. This wave function lives in a 3n dimensional space. So psi belongs to h1 of R3n. And just to give you a sense of like what the computational complexity would be like, so if we like take a nitrogen molecule which has about 14 electrons, and if we discretize this whole real line just by 10 points, we're talking about solving an eigenvalue problem with 10 to the power 42 degrees of freedom, and which is almost intractable, other than like a few tens of electrons. So this is where, in chemistry as well as in physics, people start making approximations on this wave function. And then this leads to many theories like the Hartree-Fock method, the multi-configuration equations, and so on. I won't be talking about these, but I'll be talking about density functional theory. And I want to clarify that we also saw density functional theory in one of the talks yesterday, but the density functional theory that was presented was classical density functional theory, where it refers to only atomic densities. And what I'm going to talk about over here is the quantum mechanical density functional theory. And the main statement of density functional theory is that as long as we're interested in the ground state properties, then the ground state properties are solely a functional of the electron density. And this is a very powerful statement because once this is true, then all the ground state properties can be computed in terms of a field, the electron density, which is the probability density of the electrons, which lives in a 3-dimensional space. So we have converted the problem of solving the full Schrodinger equation in a 3n dimensional space to solving for an electron density which lives in a 3-dimensional space. And the magnitude of impact of this statement has been so huge that Kohn got a Nobel Prize in 1999 for this more or less a 3-line proof.
Could you say something about why we should believe that?
Yeah, so it's a rigorous theorem actually. So it's the Hohenberg-Kohn theorem, which I'm going to like show you the proof in this. So let's say that like the state of the system is in this given by this wave vector psi. Then psi hit psi is the energy of the system, and the energy of the system is always greater than or equal to its ground state energy. So we can flip this variational statement around and say that we can compute this ground state energy E naught by minimizing over all admissible psi's of psi h psi. And I'm expanding the h over here. So this is the kinetic energy of the electrons. This is the interaction between, electrostatic interaction between the electrons. And this is the interaction between the electrons and the nuclei, which is a single electron operator. And the nuclear-nuclear repulsion is treated classically, which is in this EZZ term. So now if we look at this single electron operator, this term reduces to being integral of the electron density times the external potential. But the first two terms are still dependent on this wave functions, psi. But you can split this minimization psi into two minimizations. One minimization over all electron density, and another minimization over all psi giving a particular electron density. So now this inner minimization that we have is essentially gives us a functional f of rho. So there is an existence theorem that there exists a universal functional f of rho that describes any system, because this is solely properties of the electrons. It has nothing to do with whether you're talking about a system aluminum or you're talking about like iron or whatever it is. So this is a universal functional of electrons. The good part is that we have an existence theorem, but we don't have a representation theorem. And that's the holy grail of density functional theory. So this is where Kohn and Sham, they took this term f of rho and then split it into these three terms, where the first term is the kinetic energy of non-interacting electrons, Ts of rho. The second term is the classical electrostatic interaction energy, which we know what the functional form is. And the last term over here are all the quantum mechanical interactions, which are lumped into this so-called exchange correlation functional. And this exchange correlation functional is what is modeled in density functional theory. So this is where the empiricism comes in. But at least the good part about density functional theory is that this exchange correlation functional doesn't change from system to system. So it's the same functional for whether you want to use it for aluminum, magnesium, or some other system. And of course, there are a wide range of exchange correlation functionals available out there, but then these are generally transferable based on what material properties that we're looking at. Okay, so but that still leaves us with this Ts of rho, which is the kinetic energy of non-interacting electrons. And in cone-sham density functional theory, this Ts of rho is evaluated by actually looking at the Euler-Lagrange equation corresponding to this minimization problem, and which gives rise to single electron Schrodinger equation, which I'll get to at a different point in my presentation. And then there's the other school of thought which also approximates this kinetic energy of non-interacting electrons, and that's the orbital-free density functional theory. And in orbital-free DFT, as I mentioned, this Ts of rho is approximated. And some of the first approximations go back to Thomas and Fermi in the 1940s, where what Thomas and Fermi did is that if you have a uniform electron gas, the kinetic energy of non-interacting electrons is exactly known. So if you have a varying electron gas, they treated that particular system as locally uniform, and they used what is called as a local density approximation, and that gives the kinetic energy of non-interacting electrons that particular form. But the downside of this particular Thomas Fermi kinetic energy functional is that Teller came and showed that this is good for single atoms, but when you have multiple atoms, if one uses this particular form of the kinetic energy functionals, it doesn't predict binding in materials at all. So for material science, this is for practically not useful. And then von Weizsäcker then added a correction term, which is a gradient term, which fixed this particular non-binding in materials, and that results in what is called as the Thomas Fermi von Weizsäcker family of kinetic energy functionals. And in the last 20 years, there have been a lot of work by the chemists which tried to further improve this kinetic energy of non-interacting electrons. And one of the things that they use is that the response function of uniform electron gas is known, which means that if we have a uniform electron gas and we bring, let's say, a nucleus from somewhere, how this particular uniform electron gas responds to a perturbation in the potential is known exactly theoretically. So, and that particular response function is related to the second variational derivative of this Ts of rho. And so using that particular term, they further try to improve this Ts of rho. And I'll get to that in a little bit. So as I mentioned, this Ts of rho is modeled, but how good are these models? A variety of numerical studies have shown that these are good models for close to free electron gas systems. So these are good models for material systems like aluminum and magnesium and other simple metals, alkali and alkali earth metals. Okay, so now getting to the ground state energy functional. So the energy functional in orbital free density functional theory is a functional of U, and U is square root of electron density. So I made the substitution rho is equal to U square because the electron density always has to be positive. And so E is a functional of the square root of electron density, and this term R collects the positions of all the nuclei. So it's a vector of all the positions of the nuclei. And it has these following terms. The first term is the kinetic energy of non-interacting electrons, which in orbital free DFT, as I mentioned, is modeled. This is the Thomas Fermi term, this is the von Weizsäcker term, and these are the non-local kernel energies that I said were proposed in the past decade or 2 decades. And I'll get to the functional form of this in a little bit. The second term is the exchange correlation term, which has all the quantum mechanical interactions, and this is modeled in density functional theory, and these models are developed from quantum Monte Carlo simulations. And the last 3 terms are essentially electrostatic in nature. This is the electrostatic interaction between the electrons. This is the electrostatic interaction between the electrons and the nuclei. And these are the nuclear-nuclear repulsion energy. Now, if we look over here, all the electrostatic terms over here are extended in real space. And these involve this 1/r kernel. And it's easy to compute this particular interaction energy in Fourier space because these integrals involve convolution integrals. But Fourier space calculations have two main disadvantages. One is they assume periodicity in the system, and when we're looking at defects in materials, this is not a good assumption. It's very restrictive. And then the second thing is that Fourier space calculations involves a plane wave basis. And the plane wave basis gives the same spatial resolution everywhere in the domain. And that's not good when we are looking at defects in materials. We want to probably use more spatial resolution where necessary, and then we could potentially coarse grain far away. So it's not an adaptive basis set. So that's the second disadvantage. So that's why we sought to reformulate this whole thing in a real space. So observing over here that the extended interactions have this 1 over R kernel, which is the Green's function of the Laplace operator, we can rewrite those electrostatic interactions as the following variational problem, where we minimize with respect to all electrostatic potentials living in H1 of this particular functional, whose Euler-Lagrange equations are nothing but the Poisson equation. So we're computing the electrostatic interactions variationally by taking recourse to the Poisson equation. And now coming to the non-local kernel energies, the functional form of the non-local kernel energies looks as follows. So this is the kernel over here, and this kernel could either depend on the electron density or it could be independent on the electron density. So the chemists have developed two classes of these kernels. And if the kernel depends on the electron density, the way they treat it is by doing a Taylor expansion about a uniform electron gas. So when this kernel depends on the electron density, it's called a density-dependent kernel. But when you do a Taylor expansion about a uniform electron gas, you get a series of density-independent kernels. So I will tell you, if we have a density-independent kernel, how to treat this particular extended interaction. And then if we have a density-dependent kernel, it's just a series of these, of such treatments. So when we have a density-independent kernel, we could define a potential V alpha, which is a convolution integral of this K with u to the 2 alpha, and V beta to be the convolution of K with u to the 2 beta. And alpha and beta are parameters, which the chemists figure out through some asymptotic analysis. Now taking the Fourier transform, this would become the product of the Fourier transforms. And what Coley and Coxiras showed is that this K, which is related to the linear response function that I was talking about, could be very well approximated using partial fractions of this nature. And this is a good representation or approximation, because when we use this particular approximation, plug it in over here, and take the inverse Fourier transform, what we end up getting is essentially Helmholtz equations. So we could write V alpha and V beta in terms of these omega alpha and omega betas, which are essentially solutions of these Helmholtz equations. And these A's and B's could be complex in nature. So these are complex Helmholtz equations. And we could even recast this thing in a variational form as a saddle point problem, where we have an inf over some omega alphas and sup over some omega betas of this functional, and whose Euler-Lagrange equations essentially give us these partial differential equations. So now putting everything together, evaluating the ground state energy in orbital free DFT involves minimizing over the positions of all atoms, minimizing over all the square root electron densities U, taking a maximization over the electrostatic potentials phi, and a saddle point problem in these kernel potentials, omega alpha and omega beta. And the Lagrangian over there is as follows, and we need to do this minimization problem subject to the constraint that the total number of electrons is some prescribed n. The good part of it is that now we have a very a huge saddle point problem over here, because the number of kernel potentials over here are, depending on the accuracy that you want, can go up to 64 fields. That's the largest that we have considered. But at least the good point is that we have a local variational problem now. And so now once we have a local variational problem, if we have to discretize this problem and solve, the discretization scheme that we chose is the finite element discretization. Mainly because it allows for unstructured coarse graining. And you will see why this is important in a little bit. And the other advantages are that it can handle complex geometries, which become important when we are looking at defects in materials, as well as complex boundary conditions. And the other thing which is very important in density functional theory is that these calculations are very expensive. So we need to parallelize these calculations. And the parallel scalability is very important. And because the finite element basis has a compact support, these calculations are very well scalable. So that's one other key advantage of finite element basis. Okay, so just to see if using the finite element basis is viable or not, and if it gives us good answers or not, we computed the bulk properties of aluminum and magnesium. So we computed the energy per atom, we computed the bulk modulus and the equilibrium volume. So these are our calculations using the real space formulation and the finite element basis. These are some other independent calculations which are computed in the Fourier space by another group. And these are the calculations for cone-sham density functional theory. In all these calculations, what we do is we use what is called as a pseudo potential. So the nuclear potential is a Coulomb singular potential if we have to treat the nucleus in its full glory. But in material science, what matters is only treatment of the valence electrons. In most cases, there are scenarios where even the core electrons play a very important role. So often in density functional theory, people do what are called as pseudo potential calculations, where the effective potential of the nucleus is given by the nuclear potential and the core electrons, so that the valence electrons only can be solved for. So these are pseudo potential calculations. So this is the cone-sham density functional theory, which are the benchmark for how accurate the orbital free DFT is. And as you can see, we're in fairly close agreement in both aluminum as well as in magnesium. Okay, so then we did a more stringent test, which is trying to compute the phase stability of various phases in aluminum and magnesium. So here I'm showing for magnesium and aluminum what is the most stable phase and what is the energy of other stable phases with respect to the most stable phase. In the case of magnesium, HCP is the most stable phase, FCC is next, BCC is next, simple cubic is next, and diamond is the next. So that's the order in which it is. And as you can see, we capture the order correctly in orbital free DFT in comparison to the reference calculations of cone-sham DFT, as well as quantitatively also we are fairly close. And then we also computed the formation energies of aluminum magnesium intermetallics. And as you can see, again, the results are fairly in good agreement with cone-sham DFT. And these beta prime phases of aluminum and magnesium involve pretty huge unit cells. These have about 800 to 900 atoms in a single unit cell. Fairly, it has a long range order, but there is no short range order in these phases. And so we were not able to do cone-sham DFT calculations, but we could get to these system sizes using orbital free DFT calculations, because orbital free DFT is less expensive than cone-sham DFT. But okay, so using the real space formulation, we can probably get to about 1,000 atoms, maybe a few thousand atoms. But as I mentioned earlier, if we want to look at defects in materials, we want to get to millions of atoms, and that's the next challenge. At least a couple of times in my presentation, I mentioned that the real space formulation and the finite element basis are good because this allows for unstructured coarse-graining. We can adapt the basis set. We haven't used that feature yet, and let's see how that can be useful now. And that brings us to the theory of quasi-continuum. And I'll briefly explain what the main idea behind this is using a toy example. So let's say that we have a linear chain of atoms, and by each pink dot, I'm denoting an atom. And let's say that I introduce a defect at this end. And the defect is going to produce a displacement field in the linear chain of atoms. So the displacement field is going to be rapidly varying near the defect, but far away from the defect, it is a smooth elastic field. So we can capture this displacement field by picking some special atoms, which are these blue circles, which I call as representative atoms, and by linearly interpolating the positions of other atoms with respect to these representative atoms. So I'm introducing a kinematic constraint on the displacement fields. So we just need to use more representative atoms near the defect core where the displacement fields are rapidly varying, and where they're smoothly varying, we can use lesser and lesser representative atoms. So this is a coarse-graining idea people proposed initially in the mid-90s, which works very well for interatomic potentials. But we have a bigger problem, which is the electronic structure. So we not only have to compute the positions of atoms, but we also have to compute for these electronic fields. But there is a result by Blanc and Pierre-Lyons and co-workers, which says the following. When we are far away from the defect where the displacement fields are smoothly varying, then there is a structure to these electronic fields. And you can compute the electronic structure when the displacement fields are smoothly varying by just doing a periodic calculation using the Cauchy bond deformation at that particular point. And to leading order, that gives the right energy density as well as the right electronic structure. So using this, but this is not good close to the defect core where the displacement fields are rapidly varying at the core of the defect. So using this particular picture, we developed the quasi-continuum reduction for electronic structure calculations, where the positions of the atoms are treated in the standard classical manner, where we have representative atoms and we introduce kinematic constraints on the positions of atoms. And now how do we treat these electronic fields? The electronic fields are decomposed into a predictor and a corrector. The predictor is computed by doing local periodic calculations in these elements, which gives like a good representation for the electronic structure where the displacement fields are smoothly varying. But they're not good close to the defect where the displacement fields are rapidly varying, where you expect significant corrections. So the corrector fields essentially correct for all the errors created in this predictor, but this corrector fields are represented on a coarse-grained mesh now, because they're only going to be large near the core of the defect, and as we go far away, the predictor fields are more and more accurate, so we don't need to give the same amount of resolution for the corrector fields. So we can coarse-grain these corrector fields. So now the corrector fields are computed using our local variational problem that we have. So those are the main ideas of this coarse-graining method. And here are the hierarchy of triangulations that we use. Let's say that this is our simulation domain, and we have a defect at the center over there. So this is the mesh which captures the displacement fields. So it has full atomistic resolution close to the defect core, and it coarse grains far away from the defect core. The corrector fields are computed on a mesh, which is a subdivision of this mesh, which has subatomic resolution close to the defect core and coarse grains to become superatomic far away. And the predictor fields are computed on unit cells in each of these elements using the Cauchy bond approximation. So these are the hierarchy of the meshes that we have. And some of the important properties of this coarse graining method is that we use solely electronic structure calculations everywhere. So orbital free DFT is a single physics that we use everywhere. And the coarse graining is completely unstructured and seamless. And as I'll demonstrate, multi-million atom calculations of orbital free DFT become possible using this technique without any significant loss of accuracy. So let me first present to you the convergence of this coarse graining approximation that I just discussed. So to do this, what we did is we took a 16,000 atom domain and introduced a vacancy at the center of the domain and computed what the formation energy of this particular vacancy is, that is how much energy it requires to create this vacancy, as a function of the number of representative atoms in the domain. So as you can see, we converge, like, in the case of density independent case, we converge about like 200 or 300 representative atoms. In the case of density dependent case, about 600 atoms. So just by using 600 to 800 representative atoms, we are able to simulate a domain of the order of like 16,000 atoms. So this shows that we have a rapid convergence with respect to coarse graining in the system. But the other question is, do we actually need 1 million atoms to get the formation energy of a vacancy right? And so what we next did was to do a cell size convergence study, where we changed the number of atoms so we considered increasing cell size domains and computed how the vacancy formation energy changes with the nominal number of atoms in the system. This is the total number of atoms in the unit cell. So as you can see, we have to go to about 10 to the power 4 atoms, about 10,000 atoms, even to converge for a simple defect like a vacancy. So, and most of the calculations which are done in DFT operate in this regime over here at about 100 atoms. And then they use like periodic boundary conditions, so which means that they're not looking at an isolated defect in the bulk, but they're looking at a periodic array of defects. The interesting point, nevertheless, is that even though they were using like about 100 atoms, their converged energy was similar to our converged energy. And that kind of like perplexed us for some time. And the reason is that, like, in our calculations, the boundary conditions we use is that the corrector fields become 0 on the boundary over here. So which means that beyond this particular domain, what we have is the bulk medium. So all the perturbations coming from the defect over here are decaying by the time they come on the boundary. Whereas, so in these Dirichlet boundary conditions are much more intrusive than periodic boundary conditions. So in periodic boundary conditions, the convergence in the energy is much faster. But if you look at the fields are not converged. So it's an artificial false convergence that they're seeing when they're doing these 100 atom unit cells and see that the energy is converged, but their fields are actually not converged. So that's one point I wanted to make. And then we looked at like die vacancies in aluminum and wanted to see if we have like two vacancies put together, what is the binding energy? Do these two atoms want to like bind, do these two vacancies want to bind, or do they want to like remain separate apart? So positive values of the binding energy means that they want to bind, and negative means that they don't want to bind, they're repulsive, and then they want to be far apart. If we do like, very small calculations, you don't see any binding at all. But once you go to realistic concentrations of these defects, you actually like, see binding. And again, over here too, in the case of die vacancies too, we had to go to about 10 to the power 4 atoms to attain convergence for the energetics of these defects. So this demonstrates that we actually have to like go to large scale systems to get the energetics of defects in materials correctly. Now let me switch gears, and I want to talk about dislocations in materials, because dislocations is a very challenging calculation using quantum mechanical DFT codes, primarily because most DFT codes out there are based on the plane wave basis. And the geometry of an isolated dislocation is not compatible with periodic boundary conditions. So what people did is that they introduced a dipole, because then they can apply periodic boundary conditions. But these simulation domains are still very small, of the order of like few hundred atoms. So you have two dislocations whose cores could be like, very, very well overlapping. So it's hard to like, say anything quantitative about these calculations when one puts like defects so close. And the other way like people did these calculations is that they considered an isolated dislocation, but since they have to use plane wave basis, the geometry of this domain is not compatible, so they introduced vacuum around here. So in this case, you can get the core structure correctly, but you cannot say anything about the core energy of a dislocation, because the energetics of this dislocation are polluted by the surface energy that you have, because you have a vacuum out here. So previous DFT studies, they were able to like say something about the core structure, but they were never able to like quantify what is the real core size of a dislocation and what is the core energy of a dislocation. So these were things that were not able to be answered before. But now, since we have a real space formulation and we can apply complex boundary conditions, we could look at these questions. So what we did is the following. So we considered an isolated edge dislocation where the line of the dislocation is in the z direction, and which is along the 1, 1 bar 2, and then this is along the Burgers vector, and that's normal to the slip plane. And we considered increasing simulation domains where the distance from the line of the dislocation to the boundary over here is 2r times the Burgers vector. And this r was a parameter, an integer parameter, which gave us increasing simulation domains. And the boundary conditions that we applied are periodic boundary conditions along the z direction, because it's a line dislocation that we're looking at. And along these two directions, we applied Dirichlet boundary conditions corresponding to the Cauchy bond deformation, which means that all the perturbations in the electronic structure that are coming over here have to vanish on the boundary. And beyond that, the Cauchy bond hypothesis is valid, which means continuum theories are valid. And we wanted to identify what is the R before which, like, continuum theories are not valid and the electronic structure contributions are important. So what we did is, we did this, we computed the dislocation energy for varying domain sizes, and the domain sizes we considered is 4 times the Burgers vector all the way up to 18 times the Burgers vector. And we computed this dislocation energies. And interestingly, these dislocation energies, when we plot it, they fall on the logarithmic divergence, which is predicted from elasticity. But what we were interested in was how far are the electronic contributions important, and at what point was continuum elasticity valid. So then what we did is we computed at this delta, where the delta is the change in the dislocation energy over here when we go from 4 Burgers to 6 Burgers. So this 0.378 is the difference between this and this. 0.237 is the difference between this and this. So this is the change in the dislocation energy as we are increasing the size of the domain. And now this change has two contributions. One is the elastic energy in that particular annulus that we have, and the second is the electronic effect because we're pushing the boundary out. And so this can be estimated from Cauchy-Bonn hypothesis, again doing orbital free DFT calculation. So this is computed in full glory, full nonlinear. Because we're doing orbital free DFT calculations, it has full nonlinearity in the calculation itself. And the difference between these two is the electronic effects. And as you can see, the electronic effects are present all the way up to 10 Burgers. So it's only beyond 10 Burgers that this becomes small compared to this. Up to 10 Burgers, this is comparable to the elastic contributions. So which means that the dislocation core size is fairly large. It's of the order of like 10 Burgers, whereas most theories like continuum theories just use this to be like about 1 to 3 Burgers. So now that we have identified what the dislocation core size is from a quantum mechanical perspective, then we wanted to, so this particular calculation was done by holding the positions of the atoms fixed, because we didn't want the atomic relaxations to pollute like what the electronic contributions are. And then we relaxed the atoms, and as we all know in FCC materials, these things split into partials. And so this is the edge component of the partial, this is the screw component of the partial, and we predicted the partial separation distance to be about 12.8 angstroms, and previous DFT calculations predicted it in the range of like 10 to 14 angstroms. So we are within like what previous calculations showed. And then now that like we have identified what the core size is, we call the dislocation energy in that particular core size as the dislocation core energy, because continuum theories are not valid in this particular region. And we wanted to ask the question, is the dislocation core energy a constant, as we assume in continuum theories, or is this like, a function of something? So what we considered is we evaluated the dislocation core energy as a function of like macroscopically applied volumetric strain. And to our surprise, what we found was that the core energy was not a constant, but it was actually varying. And varying actually significantly. Of course, the strain that we applied over here is fairly large. We went up to like 5% compression to 5% tension. But the important point here is that the slope of this particular core energy is non-zero, even at zero strain, which means that it can even respond to macroscopically small strain gradients. So that's an important point. So this particular core energy has a non-zero slope at zero strain. And then we did this like for a variety of other things. Like we applied uniaxial strain. And again, in the uniaxial strain, this one direction is along the Burgers vector, and the 3 direction is along the dislocation line. In both these cases, the core energy was monotonically decreasing. But the interesting part was that when we applied the uniaxial strain along normal to the slip plane, it had a non-monotonic behavior, and it was actually increasing over here. So it shows that like actually the core energy as a function of macroscopic strain is actually a complex function of the macroscopic strain field that occurs at the core. So this is why I said that this problem is actually an interacting length scale. So if you have a macroscopic field that creates a strain field at the core, that can change the quantum mechanical interactions there, and then the core energy is sensitive to what is the deformation that occurs at the core. And we also applied biaxial strains, and even in this case, whenever we have the 2 direction involved, we have a non-monotonic response. Okay, so now if we look at, because the core energy is a function of the macroscopic strain that's coming over there, there is a force associated with it. There's a configurational force which can be computed from the gradient of the slopes of the curves that we have, how the core energy changes with macroscopic strain. This is the information that's coming from our quantum mechanical calculations, and this is the gradient of the strain that occurs anywhere. So we have a core force in addition. So if you look at a force on a dislocation, we all know that there is a peach color force on a dislocation when there is a stress field. But what these studies are showing is that in addition to this peach color force, there's an additional force coming from the fact that the core energy is dependent on the macroscopically applied, on the macroscopic strain that occurs at the core. And if there are gradients, and when there are strain gradients or inhomogeneous deformations, this core force can actually be quite significant. And so to see how, first of all, how significant this particular core force is in comparison to what's important, we looked at two case studies. One is a dislocation dipole where the dislocation, sorry? Over here? Oh, this is, no, this is a tensor, but this is contracted with this gradient. Yeah, so this is the gradient, right? So this is just with respect to x, y, z. Yeah. It's sum over i's and j's. Yeah, so this is where the gradient is coming from, and there's a sum over ij. No, so there's a gradient here. It's a space gradient. Yeah. So I'll probably come back to this later. Yeah. So so we looked at like these two configurations. One where the dislocation dipole is along the slip plane, and another where the dislocation dipole is at 45 degrees to the slip plane. And the peach color force is going to be order 1 over r, where r is the distance between these two dislocations. And the core force is order 1 over r square, because this is dependent on the gradients of the strain fields, which go as 1 over r square. So still, this can be fairly long range, because I mean it still has an algebraic decay. But we wanted to quantitatively understand how this is how relevant this is. So we computed for this particular configuration, if we compute the peach color force creates a glide force on this dislocation, whereas the core force actually creates a climb on the dislocation, just using the elasticity fields for the strain fields. And then if we look at the case where we are at a 45-degree angle, then the core force has both a climb component as well as a glide component. And then we computed this glide component and estimated how much this is going to be, and at what point will this glide component on this dislocation be greater than the Pyles Navarro force, because then the dislocations would just glide. And interestingly, what we found was that even when the distance between these two dislocations is 25 nanometers, the glide component is large enough than the Pyles Navarro force that just the core interactions can cause this dislocation to glide, which shows that like these effects are present fairly long-ranged in defects. How much time do I have? $10 minutes? Okay, so I'll quickly tell you some of the extensions that we have been pursuing towards Kohn-Sham density functional theory. And as I mentioned, orbital-free DFT is a material theory where it's only applicable to material systems where you have close to a uniform electron gas, but so it's not applicable for covalently bonded systems or ionic systems and so on. But Kohn-Sham density functional theory is much more accepted for many material systems. So the main difference, as I mentioned, in orbital-free DFT and Kohn-Sham density functional theory is the treatment of this kinetic energy of non-interacting electrons. In orbital-free DFT, this is computed this particular term is modeled, whereas in Kohn-Sham DFT, this is computed exactly by looking at the Euler-Lagrange equation corresponding to the variational problem. So when we look at the Euler-Lagrange equation, what we end up getting is an eigenvalue problem. In Kohn-Sham density functional theory involves evaluating these wave functions, which are single electron wave functions, and we have to evaluate the lowest n single electron wave functions and their eigenvalues, and the kinetic energy then can be computed from these single electron wave functions. But this eigenvalue problem has to be done in a self-consistent manner. So this effective potential over here is a functional of the electron density, and this electron density again is computed from the wave functions that are solutions of this eigenvalue problem. So this is so one has to solve this in a self-consistent manner. So that particular process is called a self-consistent field iteration of the Kohn-Sham map. And again, the ways that people have computed Kohn-Sham density functional theory previously is either by Fourier space calculation, so this is the favorite basis set for the physicists, or by using Gaussian type orbitals or linear combination of atomic orbitals, which is the favorite basis set for the chemists. The advantages of like a plane wave basis is that like if you're looking at periodic problems, it gives you spectral convergence, and it's quite an efficient basis set. But the downsides are that we cannot look at defects in materials. And the other downside is also that plane wave basis sets, when these particular basis sets don't scale well on parallel computing architectures, because when we take Fourier transforms, it is an all-to-all communications on the processors. So that's a significant hindrance that we can't throw these codes on thousands of processors and hope to like do larger problems. Whereas when we look at like the chemist basis set, like the atomic orbital basis sets, these things can only handle easily molecules or clusters of atoms which are in vacuum. They cannot handle periodic boundary conditions on the other hand. And they also like suffer from the scalability issues in parallel computing architectures. But if we look at the finite element basis, it is the best of both worlds. I mean, it gives us like systematic convergence. It gives us good scalability on parallel computing architectures. We can handle complex boundary conditions and geometries. And these advantages were known to people, physicists, for a very long time. And in fact, like physicists tried using finite element basis sets in the 1980s. And what they found was that they had to use about 1 million degrees of freedom for a single atom to get to chemical accuracy. And that was a killer, because you could get away with like a few thousands of basis functions over here. So finite element basis functions were not computationally efficient. So that was the main problem. And what we wanted to look at is when people did these studies, they only used linear finite elements. And as we know, like, the convergence rates of linear finite elements is only order h square. So we wanted to ask, if we used higher order finite elements, do we get optimal rates of convergence? And second question being that if we use higher order finite elements, do we get computational efficiency out of it? So what we did is we developed like, a series of finite elements. And when we went to like, higher order finite elements, we used spectral finite elements because spectral finite elements have better conditioning properties than the conventional Lagrange finite elements. And as just using it as benchmark problems, we considered like a methane molecule and a barium cluster. The methane molecule, we did an all-electron calculation. That is, we looked at all the electrons where the potential is a Coulomb singular potential. And for the barium cluster, we did pseudo-potential calculations where we were only solving for the valence electron. So the fields are much more smoother over here. The fields are not smooth in this methane molecule. And when we looked at the convergence, so this is the relative energy versus like the mesh size, we were getting fairly optimal convergence, both for pseudo-potential calculations and all-electron calculations. For pseudo-potential calculations, this was expected because the fields are smooth. For the all-electron calculations, this was a surprise because the wave functions live in H1, but they don't live in H2 because you have a cusp in the wave functions when you at the nucleus. But there are some French mathematicians trying to figure out like why numerically we are still getting optimal rates of convergence, and I think they have the answer. So then the second part is like, okay, I mean, we can get faster convergence like using higher order elements, but are these going to be computationally efficient? Because we have to like, use higher order quadrature rules, the bandwidth of the matrix is going to increase, and the per degree of freedom cost is going to increase. So before like looking at the computational efficiency, we also like developed like some ideas on solving this Kohn-Sham problem in a very fast manner. And to explain this, I want to go back, which I forgot to mention, is that eventually in Kohn-Sham density function theory, what matters is this electron density. And to compute this electron density, we don't need the canonical eigenfunctions, but if we have the eigenspace of the lowest n electrons, that is sufficient. We can compute what the electron density is. So we don't have to solve these eigenfunctions explicitly, but what we want is the eigenspace corresponding to the lowest n electrons. And that can be computed very effectively using this approach. So let's say we have the Hamiltonian, and this is the eigenspectrum. There is the occupied eigenspectrum that we are interested in. This is the lowest, corresponding to the lowest n electrons, and there's the unwanted space, which we are not interested in. So if we take the Hamiltonian and scale and shift the Hamiltonian such that the unwanted eigenspace lies between -1 to 1, and the occupied eigenspace lies to the left of -1, if we do that, then we construct a Chebyshev filter which grows very rapidly outside this domain, and we can apply the Chebyshev filter to a random bunch of vectors, and what that does is it kills the unwanted eigenspace and it magnifies the occupied eigenspace. So it's an extension of the power iteration in trying to compute the eigenspace very effectively. So we do this, and then we computed what the computational efficiency is for the various orders of the finite elements. So as you can see, again, I'm plotting the relative error versus a normalized time, where it's normalized with respect to the calculation which took the most amount of time. So this is with the linear finite elements, that's quadratic, that's fourth order, that's sixth order. And as you can see, these curves are moving to the left, bottom left-hand corner, which means that the calculations are becoming more accurate, and the time is much lesser. And in electronic structure calculations, the accuracies we're looking at is relative errors of the order of 10 to the power minus 5, which is much more stringent than if we were using in mechanics. And if you look at the computational advantage we get by choosing a higher order finite element compared to linear element, this is 3 orders of magnitude, which is huge. And that was the main reason why the previous attempts saw that they were not competing. So then what we did is we wanted to compare against existing highly optimized codes out there. So we looked at 172 atom aluminum nanocluster and a 666 atom aluminum nanocluster. And the time that it took for us to solve the problem is 371 CPU hours. And using a plane wave basis method, Abinit, which is a highly optimized code, it took twice the time. And in the case of this, we are probably about 10% faster. But these are old numbers with FEM. We are actually 3 times faster now. So we are competing with plane wave highly optimized codes. And then if you look at the all electron calculations, so here we're solving for all the electrons, and you can see that the electron density peaks near where the nucleus is. So this is a graphene sheet, and we are 10 times slower than Gaussian. And that is because Gaussian has highly optimized basis functions for carbon-carbon bonds, whereas the basis set that we are using is any general finite element basis set. So, and this is primarily because we needed many more degrees of freedom compared to the Gaussian basis functions. No, this is not periodic. This is non-periodic. This, as well as the previous ones, are non-periodic calculations. Yeah. And, but one thing we could still do is we could take the finite element basis and enrich this finite element basis with local orbitals that can be computed, like using single radial equations. And then our hope is that then we will be able to cut down on the finite element degrees of freedom, because we are enriching the finite element space with the known solutions of how the eigenfunctions are going to look like near the nucleus. So that's something that we're currently investigating. But if you look at the scalability, despite we being 10 times slower over here in terms of the computational time, our code scales almost to 200 processors with over 90% efficiency. And Gaussian's efficiency falls to 50% at 32 processors. So even if we don't do anything, we can just throw the code on more number of processors and hope to get to much larger and complex material systems than possible using other codes out there. And we have also been working on some linear scaling techniques. I don't have the time to discuss this, but this linear scaling technique is one of the key ingredients of the coarse graining techniques that I've discussed for orbital free DFT to even extend to cone-sham DFT. But let me just show you, so what this linear scaling technique is trying to do is the following. So in cone-sham DFT, we have to do this we have to solve this eigenvalue problem. And computing the eigenvalues scales as order n cube, where n is the number of electrons in the system. And what we are trying to do over here is to get to a close to linear scaling method, where the algorithm scales as order n. And we did these calculations. We developed this method and we did these calculations. I'm just presenting just the results. So we considered alkane chains all the way up to 8,000 atoms, and these are huge systems for density function theory calculations. And we considered aluminum clusters up to 3,400 atoms, and we get fairly good scaling. In the case of a metallic system, we get order n to the power 1.5, and in the case of an insulating system, we get close to linear scaling. And then this method also actually works for all electron calculations as well. So just to give you some ongoing works, we are trying to develop robust geometry optimization techniques. We're also incorporating more advanced exchange correlation functions, which are important when we want to look at band gaps and steady electronic properties as well. And the other problem that we're working on is to extend the coarse graining techniques that I presented for orbital free DFT even to cone-sham DFT. And I didn't have the time to talk about the linear scaling technique, but that's one of the key ingredients going into this development. And we're interested in a whole lot of like application problems, how defects like influence the energetics of defects, as well as how they influence macroscopic mechanical properties, as well as electronic properties. And I'll probably like, just skip the concluding remarks because I'm out of time, and I'll just put up like, so these are some of the publications which discuss the work that I presented. Thank you for your attention.
Questions?
So in following the calculation of charge-charge interaction, you use boundary value problem in the setup with finite element.
Right. So this is basically the Pyles solution to Pyles.
But what is the boundary condition?
Yeah. So it depends on the problem that we're interested in. So if we were doing like like the graphene sheet that I showed, like which is in a vacuum, then the electrostatic potential goes to 0, far away from this. Or you could take a boundary and then compute like what the electrostatic potential has to be even from multiple expansion. And
this is only an estimate because you are using a finite region to do computation.
Right. Yeah, but we test the convergence with respect to increasing simulation domain. So
data.
yeah.
Okay.
But if you're doing a periodic calculation, then it would be periodic boundary conditions.
Okay. Quickly, another question about this quasi-continuum.
Yeah.
In the classical, let me say, 90s, this Edmore, Philip, Otis stuff. In finite element calculations, you actually can have meshes from very fine to very coarse.
Right.
And almost continuously in a way in terms of numerical scheme.
Right.
But in your case, I think the length scale is much larger. I mean, the gap is much larger. Can you still sort of have these kind of continuous finite element refinement?
So for instance, like let me go back to the hierarchy of the meshes that I chose. So we have two meshes over here. So one is the atomistic mesh, which is similar to the quasi-continuum that you're seeing, which is capturing this displacement field. This is atomistic, fully atomistic, close to the defect core, and then coarse grains far away. So this is the continuous mesh that you were referring to. And but your point is that we also have to capture the electronic fields, which requires a much more refined mesh compared to this one. So we have like an underlying subdivision of this mesh on which the electronic structure is computed. This mesh is a subdivision of this. So the rate of coarse graining remains the same, but the mesh size is much smaller over here, and the mesh size over here is large enough that it would contain multiple atoms as you go far away.
Thank you.
How do you decide the horizon for this? How do you decide that?
So meaning like how big it has to be?
Yeah, how small, where's the horizon?
So meaning the simulation domain size itself. So we do a cell size study for the defects and try to figure out like how big we have to go so that the formation energies of these defects are converged.
So there's no way you just do it each time differently.
You have to, yeah, because I mean if you make a false assumption, then you can get like wrong physical interpretations. But it's just like 3 or 4 calculations that you have to do to see how large.
That's the big problem in the quasi-continuum method is deciding on this.
Yes.
How to match the continuum with.
Right. And there are so there are 2 aspects to this. One is how quickly you have to coarse grain for a given simulation domain size, and the second question is how large the simulation domain itself has to be. And so the coarse graining, how quickly you can coarse grain, there could be like some a posteriori estimates that one could develop. I mean, we haven't done this in our work, but it is possible to develop these a posteriori estimates where the adaptive refinement can happen and for a given simulation domain size. But how the defect energetics changes from simulation domain size to domain size, that has to be done explicitly. So you have to increase the domain maybe by order of 2 or order of 5 and then see whether the answers are changing or not.
Regarding dislocations, I'm not sure regarding dislocations.
they come up with actually finite core energies. And I don't pretend to understand how that happens, because if you use a second gradient elasticity theory, you still get an unbounded core energy.
Right.
So I found those results to be kind of perplexing and interesting in some sense. You mentioned continuum theories. Well, there are many continuum theories,
right.
including these recent ones
right.
generated by Ifantis. And I wonder to what extent your results for dislocations can be used to say anything with regard to the validity or utility of those theories.
Yeah. So these higher order gradient theories, what they do is they're regularizing the displacement field, and they get a finite core energy. But what will be really interesting is that we are computing these core energies from a quantum mechanical perspective. So it would be interesting to see how the parameters in this higher order theories are tuned, such that we can capture accurate core energies. And this is something that I'm discussing with Krishna Garikipati, who is also interested in this higher order strain gradient kind of theories.
This is precisely what I had in mind,
yeah.
is that you've got gradient elasticity coefficients
right.
that now can be in some sense tied to what's going on in the core from the electron perspective.
Yeah. And I think that's definitely something which would be very useful, because that's a way we can connect what is coming from these quantum mechanical calculations and make it useful in a large mesoscopic modeling perspective. Definitely. And then the other thing we're also looking at is to we have these core forces from our calculations. And we're trying to also put these things in dislocation dynamics codes appended to the peach color force, and then see how the macroscopic response would change. So that's one thing also we have in our to-do list.
Good idea. I was thinking about that as you were discussing it. So thank you.
Okay, let's think. Okay, you spoke of these core energies as a function of the strain gradient, but those core energies you don't know that function. It's not an a priori function.
No, but we are computing these things.
Process, doesn't it?
No, we are computing these things. So this is what is computed, and so this is the core energy as a function of the strain, and when we go to the core force, so these coefficients are what are coming from those curves.
But that function E core is not an a priori known function of the strain gradients. It depends on the process, doesn't it? It's not like a constitutive property in some sense, right?
It's what's
on the process. You do a different process, you get a different function, E core.
But okay, what we are doing over here is we're looking at an isolated dislocation. We evaluated what the core size is. We're looking at just a single dislocation. Well, we identified what the core size is, and what the energy in this core size region, we're calling it as the core energy. And then we apply macroscopic deformations, and we are relaxing. Every time we apply a macroscopic deformation, we do the relaxation. So this one actually includes this energy, this plot that I have, all these plots, includes, when we apply the macroscopic deformation, how the interior core is changing. So for instance, the partial separation distance in the edge component changes from 4.5 to 5 Burgers. Maybe I'm not answering your question, but...
Okay. That's okay. I'm having a hard time myself.
Yeah, but I can talk to you in person.
Okay. Let's thank Vikram again.